let's look at the solutions to these problems in some detail now. We're going back and looking at potential energy values, right? So in the first question here, consider the 1 kilogram block attached to the spring. It's pulled to the right. It's released from rest. This is going to end up being important to us. We'll see at the bottom of this problem. It's released from rest at position x equals positive 0.75. So we have 1/2 kx squared, 56.25 joules of potential energy stored. The kinetic energy initially is 0 because it's released from rest. We then have no potential energy at position 0. All of that potential energy that we initially started with, the 56.25, is converted into kinetic energy. So we've lost, the negative is lost the 56.25 to potential energy, but we have picked it up. We have gained it as kinetic energy. So that's how this game of energy conversion is played between our potential energy and kinetic energy values. The speed then, once I know the kinetic energy joule value, 1/2 mv squared, we can solve for v. Now, if we are told that x sub b represents the maximum compression position on the left-hand side here, and we were asked to consider that position, well, we have perfect symmetry here about the x equals 0, since the kinetic energy at position 0, right here at position 0, was the total conversion of the potential energy to the 56.25. We would expect all of that kinetic energy to be converted back into potential energy and to have the object be at position negative 0.75. That is the value we would get if we plugged in the 56.25 for the potential energy. Now, this last bit is important. If we took the object and did not release it from rest, let's say we gave it some kinetic energy. So if the kinetic energy had been 18 joules, so let's say we gave it a speed of 6 meters per second when we put it down at position A, right? So we flicked it to the left in addition to pulling the spring. We would then get a total kinetic energy based on the additional 18 joules. So as it passes through 0, the 56.25 is converted into kinetic energy, but energy is not lost or gained without friction. So no friction in this to lose energy from the kinetic energy of the object. So we now have 74.25 joules, which will be converted back into potential energy. And notice we now, as I hope we would expect, see that the block will compress further into the spring than where we started. So we can talk about this more in class if the concept of the additional kinetic energy is not perfectly clear to you. We have one more example here. So let's do it. Here we have our potential energy function, a random function. So I have no idea what's actually going on in reality. I just know this is the potential energy function that governs the motion of the particle. We're told it's a 2 kilogram particle. We're told that it is released from rest again. So that's my marble, right? I go right to my marble analogy. I put my marble down and let it roll. Notice we are told that the initial potential energy value is plus 75 joules. So that's where I got the plus 75 from. And if we were asked to describe the motion, we would just describe what that marble is doing. It's speeding up, moving to the right, continuing to speed up. That marble is going to have a maximum speed. Down here at the bottom of the trough, it's going to slow down. It's not going to come to a stop because it doesn't reach the 75 joule mark. It only gets to the 50 joule mark out here, so it is unbounded and will continue to roll to the right if the function remains as shown. So that is the first part of this. The actual joule values, as it says here, read the graph, right? So it has 0 joules at position 20. It has negative 100 joules at position 35, and then reaches back to 50 joules. Now, from 10 to 20, the change in potential energy, it lost 75 joules. Remember, the negative means lost 75 joules of potential energy. So it gained 75 joules of kinetic. From 10 to 35, the potential energy was negative 175. So from where it started to its maximum speed, it lost 175 joules of potential energy. So that was gained by kinetic energy. And then from 10 to 70, notice the difference between the between the 75 and the 50 gives us 25 joules lost total. So that tells me the kinetic energy then, as it's rolling to the right in its unbounded motion, that speed is the 25 joules, and I can calculate the speed that it has when it reaches position 70 out here. So I hope that you see how our discussion and our analysis and the use of equations is all coming together in a really neat way to be able to use potential energy and kinetic energy to describe the motion of particles, and we're going to soon put it into a more formal description mathematically.